In this set of videos, we'll discuss specialized lists called queues and stacks. First, let's recall what a list is. A list is an ordered collection of items, and each item has an index, and there is a front and a back to a list, so a first or a last element or a start or an ending element of a list. Duplicates are permitted in lists, and list elements are usually accessed by their index or position. Let's review some operations that are supported by the list abstract data type. List should permit insertion of a value at a particular position or index. They should permit the removal of a value given its position or index. We should be able to get a value at a specific location, set a value at a specific location in the list, as well as check the list size and if it's empty. In order to add elements to the list, in the back we should have pushback, which given a value will add the value to the end of the list, and find, which given a value will return the index of the value found in the list. Queues and stacks are specialized lists. Queues are first in, first out, or FIFO lists. This means that items may only be added to the back of the list, and they must leave through the front of the list. So that is push back to add to the back, and pop front to remove from the front. Stacks, in contrast, are last in, first out. We can push items to the top of the list and pop them from the top of the list. Now, when we consider the operations of the queue and stack ADTs, you'll notice that we can no longer permit insertions and removals at arbitrary positions in the list, because this would break the access protocols. Let's see what this means specifically for each. For queues, you'll notice that we cannot insert, remove, or set at arbitrary positions in the list. However, we can get the front element of the list. We can check if it is empty, its size, and we may add elements to the back of the list using push back and remove from the front using pop front. This is what maintains the first in, first out protocol. Similarly, with stacks, we may not insert or remove or set values at arbitrary positions in the list. However, we may check the top, check if it's empty and its size, as well as push an element onto the top of the stack and pop an element from the top of the stack. This is how we maintain the last in, first out protocol. Now, let's delve more deeply into queues and the Queue ADT. As we've mentioned, a queue is a specialized list that only permits elements to be added to the back of the list using push back and removed from the front of the list using pop front. This is why we refer to lists as first in, first out. The newest items are in the back of the list and the oldest in the front, and they're processed in order. We come across many examples of lists in everyday life. For example, in printing jobs in our printer, they're often in the printer's queue. When we're customers in the line waiting for the cashier or waiting to be seated at a restaurant, we're also in a queue. Queues are helpful to decouple the producers and consumers. So the consumers would be on the list and the producers will remove items from the list. Let's review the queue operations now. We have pushback in order to add an element to the end of the queue, and pop front to remove an item from the front of the queue. We can check the front of the queue by just using the front operation. This does not alter the underlying queue, and similarly, we can check the size and if the queue is empty. Now we may consider how we would implement a queue in C++. Here we have an example of a queue interface which is specified as an abstract queue class. So our class in queue is an abstract class. How do we know this? We know it is an abstract class because it contains at least one pure virtual function. A pure virtual function has the keyword virtual, and you'll notice that it also has =0 to specify that no implementation is given. Every function in this int queue class is pure virtual. It just specifies the operations of the Queue ADT. So as you can see, we have the function front, empty, size, pushback, which takes the value to add to the queue, and pop front. This is an integer queue, and this is just an example. And as you can imagine, when we get to STL containers, the queues can have any types of items in them. Now, the reason why we're specifying this interface using an abstract class is because any derived class that it would be an implementation of a queue would have to implement all of these pure virtual public member functions in order to be instantiated. Two concerns when we're implementing a queue are that it is possible to have underflow on a queue, and that's when we want to remove from the front of the queue, but the queue is empty. Another issue is queue overflow, and this is the condition when we want to add to the back of the queue, but the queue is already at its limited capacity.